Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 60. Now in the previous lecture, we were talking about the idea of zero-point energy and its significance in astrochemistry as well as spectroscopy. And we also saw that the idea of zero-point energy was illustrated through the concept of vibrational spectroscopy. So this idea of vibrational spectroscopy gave us information about the idea of zero-point energy, right? Which basically teaches us that the molecule will not be at the bottom of the well, right? Where this is the simplified potential energy surface for an arbitrarily chosen diatomic molecule, all right? So we also saw yesterday that the region close to the equilibrium bond length for any diatomic molecule, that was very well described by a parabolic potential, right? That is V of x is equal to half kx square, where k is the force constant. Now, we stopped our lecture in the previous class by introducing this form of the potential. That is, as we move away from the equilibrium region, right, the equilibrium bond length, and move towards the dissociation limit, we have to take into account this form of the shape of the curve. Now, this mathematical function perfectly does it, right? It's an exponential function of this form where d is some constant. D and a have some constants which can be fitted. I mean, that is not our concern in this course, but it can easily be done in a routine spectroscopy because you'll learn how to fix these two parameters. Okay. Now, just know that this point d, right? This term d, it needs to be having some energy unit overall because this entire term is dimensionless. So to match the dimensions, this has to be having the term d needs to be of some energy dimensions. That's it. Okay. Now, this particular potential form, right, is what is called as a Morse potential. Okay, right. So this is what is called as a Morse potential, and what it does is it takes into account the anharmonicity. Now, the idea of using a parabolic potential, right? So using V of x is equal to half kx square, right? That is what is understood as using a harmonic potential. Why harmonic? Because we kind of have a restoring motion, right? The f of x is negative k times x. So therefore, this is what is called as using a harmonic potential, and by using this potential, that is including this region of the potential energy surface also, we include by using, let's say, let me call this equation 2 and let me call this equation 1. By using equation 2, we include what are called as anharmonic effects in the molecular vibration. Okay, because by simply using the harmonic potential, we do not include the anharmonic effects. Okay, so by using a modified potential, by the way, there is no one single unique way to address this issue. We can use any type of function, but this is a widely and conventionally used function to describe the anharmonic effects. Okay, right? So we include the anharmonic effects in molecular vibrations. Now, After including the anharmonic effects also, I'm just going to call them as AE, right? So after including AE, in molecular vibrations, right, we get the energy. We call that using this particular potential, right? In the previous lecture, we did not completely derive it, but I told you that the vibrational energy, right, could be expressed as, I'll write it here, right? Using a harmonic potential, the vibrational energy could be expressed as nu plus 1/2 times h bar omega, right? We have nu is any positive integer, 0, 1, 2, 3, including 0 also. Are we good, right? So this is what we saw yesterday. But after including anharmonic effects also, the vibrational energy, right, becomes E vibe is equal to this particular term, nu plus 1/2 times h bar omega, right, minus nu plus 1/2 the whole square, right, times something, some xe h bar omega e. So see, for example, we can have this h bar, or we can also express it in terms of omega itself, okay, right? So some let's say, right? So this is going to be it, right? Where my xe, or we can call it chi, right, is what is called as the anharmonicity constant. Now what do we do? What have we done? We've simply included one more term. Recall that even in the case of the rotational motion, correct? Even in the case of rotational motion, because molecules are not perfectly rigid rotars, we had to include a correction factor, right? We had b times j into j plus 1 minus some term, right? So very much akin to that, we are adding this term right here, okay, right? And the only point to note is that your xe is a constant. It is unitless, because overall, see, this is, your nu is a quantum number, right? It's a vibrational quantum number. So this is unitless. So your omega, of course, has like units of centimeter inverse, or however you want to express it, right? So your xe therefore has to be unitless. Just note this point, okay? Now, note this point. If you recall, in an earlier lecture, we're talking about our introductory ideas to a potential energy surface, where I was talking about molecular rotation, vibration, and electronic excitation, etc. I told you that any vibrational spectrum, right, contains information about rotational spectra also, correct? Do you understand? Any vibrational spectrum contains information about a molecule's rotations also. Why is it? It is because molecular rotations are as part of molecular vibrations, okay? So I'm going to touch upon that aspect in the coming few minutes, okay? So note that molecular vibrations give us information about rotational energy states also. This is nothing new in this course. I've already told you why. Because rotational energies are part of the vibrational energies. Okay, right? So therefore, it is impossible. I'll note this. Okay, right? I'll make this statement. Now it is impossible to exclude, right, rotational states of molecules when we consider molecular vibrations. All right. This statement might sound profound to you right now if you have not paid attention, but if you've been paying attention to this class all along, it's a simple extension of what I've been saying all along. The rotational energy, for example, right? Your the region in which molecular vibrations happens, right? Molecular vibrations typically, happen around like 100 to 1000 centimeter inverse, and molecular rotations happen around 1 to 10 centimeter inverse. Again, right? I keep giving you, different units, right? Sometimes the electromagnetic spectrum, I give the units in wavelengths. Sometimes I give it in per centimeter inverse. Sometimes I give it in terms of frequencies. Sometimes in terms of energy units themselves. Okay, but they're all equivalent. Don't worry about that. Okay. So the most important point is, when you consider molecular rotation, sometimes you could get away by excluding molecular vibrations because of the separation. Okay, right? However, whenever you consider molecular vibrations, molecular rotations are always going to be part of the molecular vibrations also. Okay, so therefore we get into this scenario. I'll just play this part of the board of what is called as understanding the Rovibrational spectrum. That is, it contains information about both molecular rotations and vibrations. Okay, I'll describe what it is. And what we shall be discussing here is what is called as a Rovibrational spectrum of any molecule. In other words, because my vibrational spectroscopy provides information about molecular rotations also, I cannot decouple them. Okay, so therefore I want to include the rotational effects alongside my vibrations. Okay, to a first approximation, right? So to a first approximation, I'm going to call ERV, that is, the energy including both rotations and vibrations, as ER plus EV. Now this is going to be valid for the most part due to this energy separation, right? I can always, decouple my rotations from vibrations, in the sense that I could add them as independent terms. Okay, there could be some coupling terms, but we're not going to be getting into that right now. Okay, in some rare cases, there could definitely be some coupling, which tells us that the energy for the low vibrational aspect cannot be simply written as additive terms. It could also, include some coupling terms between this R and V. Okay, so where V is corresponding to vibration and R is corresponding to rotation. All right. So having, written it this way, my energy, my energy of this can be written as Bj times J plus 1, right? This corresponds to my ER from the previous class. And of course, see, I can also include the other terms here, such as the ones taking into account the non-rigid rotor nature, but they're not important to begin with. Okay, right? So it's going to be this plus the vibrational part, which is given by mu plus half times omega E, mu plus half the whole square times omega times some xc omega. All right. So this is the formula for the energy, including both the rotational states as well as the vibrational states. Note that I included, the anharmonic corrections. I included the anharmonic corrections, but intentionally left out. The reason why, we excluded the distortion from the rigid rotor nature, but we included the anharmonic effects is again due to this particular aspect right here. Okay, right? The distortions may be ignored, but to ignore the anharmonicity would be a more severe approximation, far further from reality. So that is why we included this term, the anharmonicity corrections, but not this. Okay. So now that we have an energy expression for the low vibrational spectrum, right? There are going to be the prominent lines. Okay, right? The prominent lines in a rho vibrational spectrum, they correspond to what are called as delta J equals +1, which corresponds to R branch, delta J equals -1. Recall from our these notations, right? Delta J, the J notations, we already were using these notations while discussing the rotational spectroscopy. So please go back to the module on rotational spectroscopy for these things. Okay, this is what is called as my P branch, and delta J is equal to 0, which is what is called as the Q branch. So these are the different types of lines, that you would be getting in a vibrational spectrum, which is also rotationally resolved. Okay. Now, note one point though. When we were discussing the purely rotational spectrum, the key point to note that when I say delta J, both the final J and the initial J, they corresponded to the same vibrational state. Okay. But here, note that the J's, right, are from different vibrational states. So this is the only difference, between the different J's when we speak of a vibrational spectrum, right, which is also rotationally resolved, versus the purely rotational spectrum, wherein we were only considering delta J within any given vibrational state. Okay, so for example, this delta J equal to 0, right? When I use this phrase delta J equal to 0, I'm particularly talking about like two aspects. One is that the J initial is going to correspond to the ground rotational state, right? Corresponding to the ground vibrational state also. This is the first aspect. The next aspect is the J final. The J final is going to be the ground rotational state of the first vibrational state, the first excited vibrational state. Okay, so please understand that. So overall, as I said earlier, these different delta J's, they correspond to different vibrational states. Okay, so these are the prominent lines which we shall see in the vibrational spectrum, which is rotationally resolved. All right, so of course, there are going to be some asymmetric aspects associated with all these branches. For example, see, we saw that in the rotational spectrum, the lines are evenly going to be spaced, right? If this was under the assumption of a rigid rotar, the rigid rotar concept holding good. However, right, sometimes, or in fact many times, and most of the times, what happens is that the rigid rotar concept is only an approximation. So there is going to be distortion. So therefore the line spacing, right, the line spacing corresponding to all these transitions are also not going to be uniform. I'm just telling you some features of this rho vibrational spectrum. Okay, that's it. So I think with this, like I'm going to end our discussion on vibrational spectrum also as relevant to detecting molecules in space. The key thing to note is that the vibrational spectrum also contains information about rotational states. Okay, right? And subsequently, there are prominent branches which are going to be given by delta J equals +1, -1, and delta J equals 0, right? And so these shall be showing up in the vibrational spectra of molecules. All right. So these are the aspects I want you to know for this course. Okay. Now, what we'll do next is, before I proceed further, I will clarify, two particular aspects from previous lectures. Okay. So clarification from yesterday's lecture. Or from lecture 59. I mean, it was a very nice question that was pointed out to me. It is that, so when we had written the energy expression, for the rotation, yesterday I had given it as equal to being, like h bar squared by 2i, right? This was the expression I had given. Okay. Now that was an imprecise formulation. it should be more precisely written as E rotation. This is for a diatomic molecule, right? So it should be expressed as like it is proportional to, because there are always going to be some constants I had left, right? So there were some constants, so we could exclude those constants. So more precisely, it is going to be proportional and not like equal to. Similarly, for polyatomic molecules, my E rotation is proportional to these three terms: h bar squared by 2ix plus h bar squared by 2iy plus h bar squared by 2iz. In other words, it was not again equal to. The imprecise version that I had given yesterday, right, was that this E rotation is exactly equal to. So please note, okay, right, this equal to is wrong. It was imprecise, and this proportionality is right. Similarly, for polyatomic molecules also, I had written the equality symbol over here. Okay, that is absolutely wrong. I corrected in this lecture. Okay, because all I wanted to convey to you was the idea that the moment of inertia, right, they can be much more complicated in the case of polyatomic molecules. The precise details, we'll soon see in a tutorial. Okay, so these are the important ideas. These are the important ideas as far as rotational and vibrational spectroscopy are concerned. And I have also corrected the imprecise statement I made in the last class. Are we good, right? So it is not equal to, but it is actually proportional to. So this is the corrected one. Whereas in the previous lecture, I had given an equal to sign over here. All right. So with this, we are more or less, like coming to the end of our discussion on spectroscopy, one part of spectroscopy as relevant to detecting molecules in space. Okay. The remaining part is what is called as electronic spectroscopy. I'll give you a brief introduction to it now. And so we're going to look at electronic spectroscopy for astrochemistry. See, now we've already looked into many aspects of electronic spectroscopy in scattered contexts. Okay, for example, some parts. So I'll just highlight what are the aspects we've already looked into, and I'll tell you how and when we shall be looking into some newer aspects. So what we've already looked into are A, as part of atomic spectroscopy. So this is what we've already seen. So what I've written here is what we've seen before. Okay, the handwriting is reasonably shabby, but sorry, yeah. So we've looked at as part of atomic spectroscopy, because we call that, even in our discussion in the context of identifying what was present on sun, right? We started off with atomic spectroscopy, although I didn't tell you the name precisely. Okay, right? We looked at what is absorption, and emission, and how this was useful in detecting atoms in sun. Okay, right? So followed by this, we also had a discussion on hydrogen atom spectroscopy, right? Wherein we in particular discussed the significance of the Balmer lines, right? And how that could be used to obtain the temperature of the star. So these were the aspects which we have already seen, and I've recalled that probably when we were discussing about the various types of motions of molecules, I've also told you that an electronic spectrum, right, it contains information about not just the change in the electronic states, but also about vibration and rotational states also. That is also something that is known to you. Now what is left is, so what we actually need to see is are what are called as selection rules. That is, what kind of transitions are allowed in atomic spectroscopy as well as in molecular electronic spectroscopy. Selection rules in atomic and molecular spectroscopy as relevant for astrochemistry. So this is something we need to look into, and we shall be doing it, in a tutorial, because there of course are going to be millions of aspects of electronic spectroscopy relevant for astrochemistry itself. Okay. However, given the limited time that we have in this course, we shall be discussing the selection rules. We've already looked at what are called as gross selection rules, remember, right? Whenever I was introducing you qualitatively to the idea of transition moment integral. Now, we're going to amp it up a notch further, and we're going to be talking about more precise selection rules, right? Which could be derived from the transition moment integral by computing the transition moment integral, but we're not going to compute any integral in this course, okay, right? I'm just going to give you the final result, and as part of it, we should also be seeing what are called as, shall discuss the term symbols. Okay, right, for the atoms and not all the polyatomic molecules, but perhaps the diatomic molecules. So this will be very soon done in a tutorial. So with this, our discussion about spectroscopy as relevant for astrochemistry is coming to an end. So what we'll do further in this course is, we shall next look into the astronomical part, okay, right? See, this is spectroscopy is one part of detecting molecules in space. It's actually astronomical spectroscopy which gives us the full picture, right? So we'll look into the astronomical part of astronomical spectroscopy in the upcoming lectures. But before that, we shall be having some tutorial sessions wherein I shall elaborate upon the selection rules. I'll also elaborate upon the different aspects of selection rules associated not just with electronic spectroscopy, but also with rotational and vibrational spectroscopy. And I'll give you a preview about the various types of moments of inertia. Okay, right? That I think I promised I'll inform you in lecture 59. All right. So on that note, I conclude this lecture, and I shall see you soon in the next lecture. And before we leave, I hope you all clear about what all we saw today. We discussed about the vibrational spectrum, right? As pertinent for astrochemistry. We understood that as part of a vibrational spectrum, we also get information about the rotational states, and the prominent rotational lines are going to be what are called as the delta J equals +1, which is called as the R branch, the delta J equals -1, which is called as the P branch, and delta J equals 0, which is the Q branch, right? And noting that these delta J's, the J's and delta J's correspond to different vibrational states. And after that, I gave you a summary of what all we saw as part of electronic spectroscopy in this course, and what we shall be seeing soon in the tutorial. On that note, thank you all. Thank you.